Okay, welcome to lecture. We'll get started here in just a second. So we are starting on the last chapter. That's good. So again, these notes should be up online on the Canvas site if you need them. I'll just give everybody a minute or so here, and then we'll get going. Okay, so let's get started. So this is going to be the last chapter, which is always a good thing. So the last thing we're going to talk about here is kinetics in this semester. And a reminder again, as we talked about last couple days, exam again going to be on Monday. So today will be a regular day. We're going to lecture, and then we actually have the colligative properties, I think, experiment, boiling point. So that would be good review for Monday as well. All right, so this should be chapter 11, which is chemical kinetics. Let's talk a little bit about sort of kinetics, obviously. So a couple of things, a couple of sort of big sort of topics that we usually talk about in chemistry are thermodynamics and kinetics. Although in this class, since they sort of took out chapter 6, I think it is, that has to do with energy and stuff like that, which is part of thermodynamics. You'll mainly talk about thermodynamics if you continue on to take 200B. But sort of the area of thermodynamics, our study of thermodynamics really deals with the idea of whether or not a reaction will take place. So usually when you're dealing with thermodynamics, and again, if you take 200B, you'll learn obviously about enthalpy a little bit more than what we talked about here in this class. Things like entropy, things like free energy. And a lot of those things deal with the idea of, like it says there, whether or not a reaction will actually take place. And if a reaction, for example, is spontaneous. And sometimes when people think about reactions being spontaneous or taking place, sometimes we think about it, oh, it must just occur super fast, like right away, always occurs kind of fast and occurs. And as you'll learn in the next semester, if you do take it, thermodynamics or spontaneity doesn't necessarily mean that the reaction will occur super fast. It may occur fast and also may occur slow. May occur sort of moderately in terms of speed. So the area of thermodynamics, which again, sort of talked about a lot more next semester for you guys, most of you, deals with that idea, just whether under these conditions, would we expect this reaction to actually occur? And again, it has really no information about how fast or how slow the reaction will occur, just whether or not it will sort of take place. And how fast or slow a reaction will take place is really the area of study, which is kinetics, which is what we're going to talk about in this chapter. So kinetics does focus in on sort of how fast or, how slow a reaction will take place. And again, that's sort of what we will deal with here. So when we talk about things occurring in terms of a reaction, fast or slow, there's usually a couple of things that we're usually interested in normal sort of chemical kinetics. In chemical kinetics, which are basically just your basic chemical reactions and stuff occurring, we're interested really in usually molarity and how the molarity or the concentration is changing over a period of time. So that's really what we talk about when we talk about a reaction rate, which is how the reaction is changing over a period of time in relationship to the concentrations of our reactants, perhaps the concentrations of our products, how they are changing. So the change in that is what is sometimes referred to as the reaction rate. And that's why we do see these units associated here with reaction rate, which is molarity over seconds. So molarity here is the same molarity we've been talking about all semester here. Obviously, that is moles per liter. So what we're looking at in sort of a kinetics reaction is over a period of time, how is that concentration of either that reactant, that product sort of changing? And when we look at a reaction, and in most cases, when we look at a reaction like this of A going to B, we are assuming that pretty much it's a one-way street since we have a one-way arrow. So, the entire reaction is basically heading, in that direction. And what we know, if we just think about it sort of logically, if the reaction is heading towards the product side, what we could imagine is we would expect over a period of time to see our reactant concentration should start to decrease, right? So if this reaction is heading to the right-hand side there to make products, in order to make the products, we have to kind of use up some of our reactants, or a lot of our reactants. And then obviously on the other side, we would initially assume that we most likely have nothing going on there. So as the reaction proceeds and those reactants become products, that we should see a increase in the amount of products that are being made. So, logically speaking, if the reactions go to the product side, we have to make products. So to make products, you need to use your reactants. So reactants should come down. Product concentration should then go back up, coming out the other way as the reaction proceeds. And we could write a relationship that explains what's going on in a reaction in terms of that, in terms of sort of kinetics and reaction rates. And these guys here are what is sometimes referred to as rate expressions. So these guys here are sometimes referred to as rate expressions. And, it's really sort of a calculus expression here, but basically we have sort of the change in the concentration of A over the change in time. And again, a reminder that if you see these brackets, it does mean concentration. And again, usually that means molarity. So what we have there is the change in concentration of A over the change in time. And we also have the change in the concentration of B over the change in time. Now, there is sort of a difference between those two things, and the difference comes here with what is circled, and we do have negative, the change in the concentration of A over the change in time, but we don't have the negative in the bottom guy. And the idea behind that is that the first one there, A, is a reactant. So as we just talked about, over a period of time, we would expect the concentration to come down. And that is why we see the negative there. While on the product side, as we talked about, the concentration should come back up. And it's represented by sort of a positive change that occurs, so we don't put the negative sign there. That negative sign is also really important because when we calculate something like the rate of a reaction, like this guy here or this guy here, which by the way would be the same number for this reaction because it's the same overall reaction that's happening. This is what is sometimes referred to as the average rate for the overall reaction. And this number here should always be kind of a positive number. And that's why the negative here is really important, because if A's concentration is going down, so for example, let's say we started with A having a concentration of 4 molar. By the end of the reaction, it should be going down. So let's just say we didn't let it go all the way to 0, but let's just say it ended at 2 molar, right? So this was like our initial, this was our final. So when we do the change in A part in my made up numbers, it would be our final, which is 2 molar, minus our initial, which was 4 molar, gives you minus 2 molar, right? So that minus there that you would get from the calculation from the inside part, and this minus here that goes with the formula will turn your rate into a positive number. You don't need that for the bottom guy, because the bottom guy, their concentration should be increasing with time. So initially, if you had for B 0, and you finally had at the end 2, when you do final minus initial, that is 2 minus 0, which is positive 2. And again, you don't need to adjust it or anything like that. So that is why that negative is there for our reactants. Again, overall decreasing with time. And as you do final minus initial, that's going to give you a negative number. And again, that negative will then turn it into a positive number. So this is a way that if you have some type of piece of information about a reaction, maybe how the reactants are changing with the period of time, maybe how products are changing with the period of time, or if you just have kind of the overall rate, you can basically figure out how everybody else in the reaction is changing. So how do we look at sort of rates happening? Again, here you can see visually up on top the circles. The black circles there look like A, the red circles are B, and you can see that when the reaction begins over here, pretty much all reactants, yeah, well, all A. As the reaction starts to go, we see that the black circles are going less, red circles are getting more, so we're starting to produce some products. So we have A and B, and we have A and B all the way through here, but you can start to see a greater amount of the red circles happening, so kind of a greater amount of B as you come this way, and so forth. And that's what we see graphically. And since it is kinetics, a lot of times you will see graphs in this chapter. You'll see a lot of tables of experimental information. But just visually, what we see here is the same thing. At the start of the reaction, we pretty much have 100% of our reactants. We have none of our products, which is represented by the red line here. And as the reaction proceeds, our reactants start to decrease with time. So we see a decrease in that, and an increase in our products here as the time goes on. And again, that's sort of what is happening here, as you do need to use your reactants to make your products. So how do we sort of in the laboratory follow sort of kinetics? And there's a couple of common sort of ways that we can follow kinetics or look at kinetics. And one very common way is sort of using absorbance and using something very much like that Kool-Aid experiment, for example, where you use something like a spec 20 or spectrophotometer, and we can measure the absorbance values. And one thing that you should be familiar with as well is the absorbance idea is the darker the solution, right? So the more color the solution has, the higher the absorbance value will be, right? Absorbance is basically how much light gets absorbed by the solution versus how much gets to the detector. And that is related to sort of the color of the solution. So again, darker solutions will absorb more light. Kind of lighter solutions to colorless solutions, the absorbance value goes down a lot. More of it is being transmitted through the solution rather than being absorbed. And in a reaction such as the one sort of written out here, the BR2 is really the thing that's providing the color that we see here. And all these guys on this side is pretty much colorless. So just visually looking at it, we can see that as time goes by, we are moving ourselves towards the product side, which are colorless in terms of color, I guess, which is not much of a color. And we could use something like absorbance and like Beer's law, which is our, you know, A is equal to BC, A being our absorbance, B being our Beer's constant. And the Beer's constant is that molar absorptivity and the path length, and C being concentration. And by basically measure the absorbance value over a period of time, we could basically figure out how the concentration of something is changing, like BR2 in this case. This graph here also should be a familiar type graph to you. This is like what the spectromaster person there in the Kool-Aid experiment did, where you try to find your maximum wavelength, right? So your maximum wavelength of absorbance. And the purpose of that, as well as we talked about back then when we did the sort of that experiment, the purpose of choosing a maximum wavelength of absorbance is to allow, obviously, when you do the experiment, all your samples should really, fall within the area of being able to be read. Again, if your maximum absorbance where I circled and you decide to set the wavelength to over here, you pretty much are going to get nobody to give you values. They're all going to be above sort of the area where it will maximally absorb. And because absorbance is related to concentration, especially when we have solutions that have colors associated with it, by following the change in absorbance values, and you can use something like Beer's law to basically convert absorbance into concentration, we can follow how the concentration, for example, of BR2 is changing with time by following that absorbance values. So that's a really sort of easy method and a very common method to do sort of kinetic studies in the laboratory, especially when, like I said, there's some type of product that has a color, either a product or a reactant. Usually in most cases, it will be starting with a reactant that has color, and then it kind of goes away, is usually the case in terms of kinetic studies. So you know that the reaction has begun, because when you mix it together, you can actually see the color. So you know you did everything correctly. Obviously, if you went the other way, you could still do it, but you have to kind of wait for the color to appear before the absorbance would happen. So usually we start with a reaction where if you mix kind of two things together, you get this color develop, and then you wait for the color to kind of disappear. Now, when we're measuring something like this, so for example, in that reaction that we were just looking at, we would get a graph, perhaps something like this over time, the change in concentration. And as we can see, we do see sort of that decrease in the concentration over a period of time, which is what we would expect. Again, our reactants should be being used up to make our products on the other side. And when we talk about rates, there's sort of two different types of rates that we sometimes refer to. One is an average rate, and that usually is sort of the rate for the overall reaction over the entire sort of reaction that's occurring. And again, we can find that by taking, in the case of BR2, the change in the concentration of BR2 over the change in time. Again, we do have our negative here because this is a reactant. And when we do this calculation right here, this number is going to end up being negative no matter what you do, because you can see from the graph, the BR2 concentration is decreasing with time, which means whenever you do final minus initial, the final will always be lower than the initial concentration. So again, going to give you a negative number. And then again, that extra negative turns your average rate into a positive number, which it should be. So again, this guy should be a positive number when you do that. So when we talk about average rate, it's usually for like the overall from beginning to end of the reaction. Now there's something that's known as sort of a instantaneous rate, and an instantaneous rate is sort of like a snapshot of your rate for a period of time. So it's a specific rate for a specific period of time. And, you could find that a couple different ways. You could do like the slope of the tangent, as you can see there, for that period of time. Those are the rates that are happening at that specific period of time. So you can sort of think about average rate versus instantaneous rate, kind of like when you drive. So for example, if you're driving from here to say Arizona or something like that, and if you drive, say as a whole, at some points in the trip, perhaps you're doing 65, Maybe some points you're doing 70, some points maybe 75, which is like the speed limit when you get out into Arizona. Maybe 80-ish, hopefully not too much higher than 80, 85, not 90 or something like that. But, you know, at different periods in your trip as you're driving, there might be an instantaneous section there where perhaps you're driving faster and some parts where you're maybe driving slower. You know, hopefully the police officer is not behind you while you're instantaneously driving 90. But, you know, if you average out your entire trip, for example, you know, from beginning to end, your average rate, you know, or your average speed may be, you know, maybe it was 67 miles an hour or 65 miles an hour or something like that. But again, there's instances in that trip or that specific period of time. If you just kind of take a window snapshot of how you're driving, you may be driving faster, you may be driving slower than say 65. And that's sort of the idea here with instantaneous rate. If you kind of take just a snapshot of the reaction, you know, there may be periods where it's sort of reacting faster. Maybe there's periods where it's kind of the rate's a little bit slower. But then when you sort of average everybody together along the way, you get sort of an average rate, just like you would have sort of your average, you know, miles per hour you drove on your trip. So when we look at some information here, and again, this is a typical type table that you will see in sort of kinetics. And there's a couple of important information from these tables. This information may be not given to you usually in a table, but you know, we have the concentration, we have the time, we have the rate, again, at the sort of those specific areas, those instantaneous rates. And there is a relationship that develops that is a constant relationship that occurs for a reaction. And that is given by lowercase k, this little k. And I say little k because if you do take the next semester class 200B, you'll talk pretty much all about, I'll write it like this, big K, which is the equilibrium constant. And that is not what we're talking about here today. We're talking about little k, which is known as the rate constant. So the rate constant is basically a constant value for a reaction under a specific set of conditions and temperature and all that. That basically will give you, obviously, as you can see here, a constant relationship as you go through it in terms of how fast, for example, a reaction is taking place. Here, where you look at sort of the instantaneous rates, they do vary depending on sort of the section of time, but there is that relationship of the rate constant, which, as the name implies, is a constant value for, you know, you can kind of use it for how fast or slow a reaction is sort of taking place based on the value. The rate constant comes from what is known as the rate law, and this is what a rate law generically looks like, and we'll talk more about it later in this chapter. But this is basically what a rate law looks like. The rate of the reaction, that's your rate constant, and that's your concentration of your reactants here. And you can see again, we have a pretty constant sort of number when we look at the rate constant that's happening. And if we sort of rearrange the rate constant and solve for K like they did over there, K equals the rate divided by the change in the concentration of Br2. And if you look at this graph, that is rate on the Y, change in concentration on the X. And if you remember a straight line formula, Y equals mx plus b. Y is what you graph there on the Y. X is what you put on the X. B is your y-intercept. And m is your slope, right? And your slope, as you may know, is rise over run, right? Which is rise is our y over run, which is our x. So that is the rate over the concentration of Br2. So graphically, if you took this, you could take the slope and it would equal the K value in this particular case from that particular line. Now, not all reactions will generate something or start with something that has color associated with it. And an idea that you also should be familiar with is the idea that in order to use something like we were just talking about, something like absorbance values, you do need some type of color to sort of follow. So obviously, if you did a reaction where there really is kind of no color that develops, it makes it really hard to do a sort of a kinetics experiment using absorbance values, because you're going to get zero absorbance all the way through. And obviously, that's not going to be extremely helpful in trying to determine things. So if we look at, for example, this reaction here, what we got going on is essentially a pretty colorless type of reaction. So absorbance values probably wouldn't be so great to do it, even though the flax looks yellowish here. It's some other stuff in there, I think, for you to see what's going on in the picture. But pretty much colorless going on here. That's hydrogen peroxide, so you've probably seen hydrogen peroxide. Doesn't usually have too much of a color. Water and oxygen gas, they have no colors associated with it. So this is sort of a colorless sort of reaction. So absorbance values wouldn't be so great to do. But we are generating here in this reaction a gas. And when we talk about gases, we think about the ideal gas law. And one of the things that we talked about with the ideal gas law is if you do some rearranging really of the ideal gas law, and for example, you solve for N over V equals P over RT. And the reason why we might be interested in solving for N over V here is N, again, in the ideal gas law is moles, V is liters. So that, again, as we talked about, I think when we were doing gases as well, that is essentially molarity. And you actually can figure out the molarity of a gas and thus also figure out how it's changing by following a very simple thing. If you just think about what you're going to be solving for here, R is a constant. And if you, excuse me, if you did this reaction, most likely that temperature is going to remain constant for the reaction. So really the only thing that you would need to sort of follow in a reaction like this would be the pressure change. And that you could easily be done by sort of a setup like this, where the gas kind of comes in, the pressure, the mercury starts to rise. You can basically take some readings as to how the pressure is changing over time. And that allows you to follow basically one sort of variable, which is pressure. And using some calculations here, you could turn that into basically the molarity of the gas. So why would the pressure change be important in a reaction like this? If you look at a reaction like this, the only gas that we have is this guy here, right? Which means since that is the only gas that is present, it needs to be present to actually see pressure occur, right? And pressure starts to change, which means we know that this reaction is actually occurring once we start to see some pressure, right? Because if we have pressure, that means we have a gas there. And the only gas that could be there is oxygen gas. And that oxygen gas in this case could only have came from the hydrogen peroxide. So by following the pressure, we know that this reaction is actually taking place, because we'll start to see the appearance of pressure occurring, which would indicate that we do have obviously gas being occurred, and this reaction is actually taking place. And as I mentioned, doing some manipulation of sort of the ideal gas law, you could basically solve for how the concentration of O2 is changing with time. And again, basically, you're just going to be following pressure, because as I mentioned, these guys probably will remain relatively constant for this type of reaction. So if you follow the change in pressure and you do it for the time as well, we now have a way really to follow the appearance of O2 over time. So this again is our rate expression, which is the change in the concentration of O2 over time. This is a product, so again, going to be positive here. And ultimately, as you can see here, as we've just been talking about, these are really the two things that you're really going to be following. Again, that change in pressure and that change in time that's going to occur. And again, this creates a way where if you have a reaction that, again, doesn't generate a color solution or doesn't start with a solution that's has a color associated with it. Again, this is another sort of way that you can perform a kinetics experiment. Any questions on that there? And this would just be sort of a graphical representation of this. And as we can see, over time, we see an increase in pressure. So again, at the start of the reaction, we have pretty much no pressure, which would indicate obviously that there is no oxygen gas there. And as time continues, we do see a pretty good jump here in the pressure. And that would imply obviously that we are making some O2 to obviously do that pressure. Also would secondarily imply that the reaction is actually taking place. So let's talk about, though, when we talk about reaction rates and sort of reaction expressions, we do have to think about our favorite thing, which is stoichiometry. And stoichiometry, right, is the mole-to-mole relationship that's occurring in a particular chemical reaction. And it will have some effect on the reaction rate or how things change over time in terms of reactants or products, is sort of that mole-to-mole relationship. So if we look at an equation like this that's balanced, just like we normally do, we could sort of do that mole-to-mole relationship and say for every 2 moles of A, we get 1 mole of B. And how that will affect something like the rate expression is we do need to sort of incorporate that into the rate expression to really take care of sort of the mole-to-mole relationship between everybody, so that we sort of get the right proportion that's going to happen in this particular reaction. So for this particular reaction, we would write that the rate equals -1/2, the change in the concentration of A over the change in time. So where the 1/2 comes into play is what we usually will do is take 1 over the coefficient. And that will allow us to take into account the stoichiometry. So really this part here is for that mole-to-mole relationship. And it is simply 1 over the coefficient. And we still have the same things that we've been talking about. We have the negative here because he's a reactant. So that is -1 over the coefficient, which is 2. Change in the concentration of A over the change in time. We would also do the same thing for our product. The rate would equal, again, it's a product, so it's going to be positive. The coefficient here is 1, so we don't really write it, but technically it's 1 over 1, which is 1, which is why there's no 1 over in this case, because it's basically 1. Change in concentration of B over the change in time. So generically speaking, you can use this to get the proper mole-to-mole relationships when you're looking at a balanced equation by basically taking 1 over the coefficient. And we could set all of those kind of individual rate expressions equal to each other. So the rate equals, in this case, -1 over A. Again, A being a reactant, so that's why the minus is there. The change in the concentration of A over the change in time equals -1 over B. Again, B being a reactant, also going to have the negative there. Change in the concentration of B over the change in time equals 1 over C, change in concentration of C over change in time. Again, C being a product, so increasing with time, no negative on that side, equals 1 over D, also a product, so also increasing with time, no negative, the change in concentration of D over change in time. Now, you could use these all equal to each other. You can break them up like they sort of did up here, where they just took them individually. Again, the rate here and the rate here will be the same number for that particular reaction. So again, you can set them all equal to each other like down here. Or if you're just interested, say, in B, you could just pull that part out and go the rate equals -1 over B, change in the concentration of B over the change in time. And again, you could kind of pull it out or keep them together depending on what you need to do. Usually a lot of times it's easier to kind of pull out each of the pieces that you need and then sort of put them together at the end. The usefulness of this sort of relationship is it pretty much allows you to get a pretty good idea as to what is happening in a reaction. And really all you need is kind of one piece of information. So if you know the overall average rate, that would allow you to figure out how each of the reactants are changing, each of the products are changing. If you have an idea as to how the product is changing over a period of time, that would allow you to figure out how the reactants are changing. That will also allow you to figure out the average rate for the reaction, you know, and all that kind of stuff. So it's a very useful way to, you know, really get a handle on how a reaction is changing over a period of time. And you really need sort of minimal information about somebody in the reaction, and will allow you pretty much to relate it to everybody that's going on in that particular equation. So why don't you take a second here, or why don't you write the rate expression for this and see what you come up with, and then we'll talk about it. Okay, so let's take a look and see. So the rate expression, again, is what we've been talking about. So here we would start with the rate is equal to, we'll start with our first reactant. Again, because it's a reactant, we're going to go with a negative. It is going to be 1 over the coefficient. So again, the coefficient here is 1, so it's going to be 1. Typically, you don't put the 1 like most things. So this is going to be the change in the concentration of CH4 over the change in time. This will equal to our next reactant, which is our O2. So again, because it's a reactant, we're going to go with a negative here. It does have a coefficient, which is 2. So we're going to take 1 over 2, which will help us with the stoichiometry part of it. The change in the concentration of O2 over the change in time. Now we're coming to our product side. So again, these guys should be increasing with time. So no negatives, technically positive. Also has a coefficient here of 1. So it's going to be 1 over 1, which is again 1. So this is going to be the change in the concentration of CO2 over the change in time. And lastly here, our last product, also a product, so going to be positive. It does have a coefficient. So again, we want the 1 over 2 for the stoichiometry part of it. And it will be a change in the concentration of H2O over the change in time. So this would be sort of the rate expression. Again, you could set them all equal to each other like I did here. Or you could write individual expressions where you just do, you know, each of them sort of equal to rate. Yeah. And again, as I've been mentioning, these two numbers are going to be the same. And that's why, because they are the same for the average rate for the reaction, that's why we could set them all equal to each other, because they all technically will equal the same overall average rate, because technically they're all in the same reaction. So that's why we could do that. Any questions on how to write a rate expression? Now, let's take a look at one and give you a chance at it here. Let's do one where we actually have some numbers and some calculations, and let's see what you come up with. So let's take a look at this one here. For a reaction, given that the I minus changes from 1 molar to 0.868 molar in the first 10 seconds, calculate the average rate in the first 10 seconds and the change in the concentration of H plus over the change in time. So we're looking for sort of two answers here. And why don't you give it a try first and see how you do. Again, start with the rate expression and then actually insert the numbers and see how you do. And then we'll talk about it. Okay, so let's take a look and see how you're doing. So I personally, when I sort of approach these type of problems here, what I'm looking for is a good place to start is to really just pull out the two things that you sort of have either information on or what you're trying to solve for. So, and sort of ignore obviously everybody else in the equation. Again, you really want to kind of focus in on those two things. And for this particular problem, we're given the concentration of I minus. So we're definitely interested in I minus here. So we would want to maybe start with the rate expression for I minus. So the rate would equal minus, because it is a reactant, 1/3 for the coefficient, change in the concentration of I minus, so run into there, over the change in time. Now, you may also want to write the rate expression for the other thing that we're interested in, which is also the H plus over time. So H plus is right here. So for that guy, the rate equals, again, also a reactant. So it's going to be minus 1/2, the change in the concentration of H plus over the change in time. So Just clean this up a little bit here. Perfect. So these are our two rate expressions that we could deal with here. And in terms of both of these, we pretty much have enough information to go into here because we have how I minus is changing over time. We don't have the information to go into here yet, but we could use what we get on the left to help us on the right, and we'll see that here in just a second. So since we do have the information here for our guy on the left, we could go minus 1 over 3. Now, for our I minus, we want to do the change in the concentration. So this is our final concentration. The 1 is our initial concentration. So here we would take our final, which is 0.868 minus 1. And for our time is 10 seconds. So technically speaking, probably 10 minus 0 in terms of seconds, right? And if we do that, what we end up with is number. And if I actually type in the right number, that might help. Let's try that again, divided by 10. I'm not sure where I divided by 8 for, but we do get a number of 0.0044. Units here are molar on top and seconds on the bottom. They have not canceled, so molarity over seconds. And that actually is one of the answers that we're looking for. That is the average rate, right? What we just solved for. Any questions first off on that calculation? Again, you can see sort of with numbers now, hopefully, what I was talking about, because our final concentration here is less than our initial. When we do that subtraction part, we get a negative number, and that is why we have the negative here. Those two negatives are going to turn our rate into a positive number, which is what we're looking for in this particular case. Now, we do have a second thing we're looking for, which is this. We're looking for the change in the concentration of H plus over the change in the bottom. Are you talking about over the units? That's molarity per seconds. If you're talking about on the over here, that is 10 minus 0 seconds as well. Is that, I think, what you're talking about? I think the question. Okay. So the second thing that we're looking at is the change in the concentration of H plus over the change in time. And that's where we can use now our second sort of relationship to help us out. So again, if we rewrite it, the rate is equal to minus 1 over 2, the change in the concentration of H plus over the change in time. And what we are actually trying to solve for is this whole thing, right? The good news is why we needed this is this number, which we just got, is the same as this number. So by solving for the average rate here first, because we had an information about I minus, that now allows us to have the rate number for this guy, which means what we need to do is take 0.0044 molar seconds would equal minus 1 over 2, the change in the concentration of H plus over the change in time. And again, since we are solving for this, you should hopefully be able to see we need to multiply the 2 to the other side. But more importantly, not just the 2 needs to go to the other side, we need to multiply the negative as well to the other side. So when we do that, we end up with a, if we multiply that 2 to the other side, we end up with the change in the concentration of H plus over the change in time as being minus 0.0088 molar seconds as how this guy is changing. So again, to get there, 0.0044 molar seconds times negative 2 from the other side, H plus over change it. And again, this 2 is doing that stoichiometry part for us. And you can see here we get our change. And this also makes sense if you think about H plus, as we've been talking about. H plus is a reactant, so we would expect it to be decreasing with time. And the representative of that is we do end up with a negative value here for how the reactant is changing with time. And that negative value again means that it should be decreasing, which is what we would expect to happen. Any questions on that calculation there? So basically what this is saying is for the H plus in this concentration, in this reaction, over a period of time, it is basically decreasing by 0.0088 molarity every second. So every second it drops 0.0088 molar. And what it is saying as the rate of the overall reaction, how fast overall the reaction is taking place, is there's an overall change of 0.0044 molarity per second. So what does that mean? Like, well, the one guy is changing 0.0088 per second. The average rate takes into account, obviously, how all 3 reactants in this case are changing in relationship to how much products we're making over that same period of time. And again, you get that average value for how everybody is changing sort of overall in the reaction. Any questions on that? All right, so why don't you try another one here. 2.4 times 10 to the 2 grams of NOBr decomposes in a 2 times 10 to the 2 milliliter flask in 5 minutes. Find the average rate of Br2 production in molarity per second. And they were nice enough to give you the molar mass there, which is 109.91 grams per mole right here from the periodic table. All right, so take a couple minutes, see what you come up with. Again, approach it the same way. Use the information that's given to you and then try to relate it to, in this case, the Br2 and see what you come up with. Okay, so let's sort of work through this here. So again, kind of taking the same approach, figure out the sort of rate expressions for the things that we're interested in here. So obviously we have information about NOBR, so we could write the rate expression for that guy. The rate is equal to, again, minus, because it's a reactant, 1/2 for the coefficient. And again, the change in the concentration of NOBR over the change in time. We're also interested in our BR2 eventually. So for that guy there, the rate is equal to, coefficient is 1, so we don't need anything. Also a product, so going to be positive. This would just be the change in the concentration of BR2 over the change in time. Now the difference here is we don't have the kind of the initial and the final here, but we do know that it's going to decompose and go through a decomposition reaction, which would imply that it all gets sort of used up. So we do have enough information to figure out the molarity here. We have the grams, we have the molar mass, which we could get the moles from. We also have the volume, right, which we could get the liters from. So if we do that, we would take probably first 2.4 times 10 to the 2 grams of NOBR using the molar mass that was provided to us. And again, if it wasn't provided to you, you could go to the periodic table to get that. That is going to get us 2.4 to the 2, divided by 109.91 gets us 2.184 moles of our NOBR. This is essentially 200 milliliters, right? So 200 milliliters, 1,000 milliliters in a liter gets us 0.2 liters. So obviously we now have the moles and we have the liters. So we could find the molarity of the NOBR by taking 2.184 moles divided by 0.2 liters. Gives us 10.92 molar as the molarity there. Hopefully that should make sense to you. Again, that's just basically finding the molarity like we've done hopefully a number of times at this point. The purpose of doing this is because that's essentially going to be our top number here in our change part. We still also have the bottom number, which is the change in time. This is going to be done for 5 minutes. And I'm going to do a conversion here because when it's all said and done, in terms of time, I'm not looking for minutes, but I'm looking for seconds, which means at some point you have to do a conversion, obviously, from minutes to seconds. So I'm just going to do that up front to kind of get it out of the way. So that means I have 5 minutes. And I believe a minute is 60 seconds, hopefully, right? And that's going to give me 300 seconds. So now I have the bottom in the right units, I have the top in the right units. I now have everything I need to go into this expression for the NOBR. And if I do that, the rate will equal minus 1/2. Now my change in concentration is going to be negative 10.92 molar divided by my change in time, which would be 300 seconds. And if you do that, we end up with 0.018 molar seconds. Now you may ask yourself, why did I make it negative here? And I made it negative here for a specific reason. This is a reactant, which means we know that the final concentration of that reactant will essentially be less than the initial concentration like we've been talking about and should give us a negative number. In this particular problem, they kind of just did the final minus initial and sort of gave us the overall that's going to happen. So if I did not make it negative, what I would have ended up with for my rate is a negative number. And as we talked about, you cannot have a negative rate. So the overall average rate, so when we specify that when you solve for the average rate, which is what that rate is there, it should always be a positive number. So that's why we had to insert kind of the negative there, because technically speaking, it's a reactant. So the change part should be negative no matter what the situation is for a reactant, just like the change part should be positive when you go to the product side. So now we can relate this to the BR2 using our rate expression. And again, we see that the rate is equal to the change in BR2 over the change in time. And we just calculated the rate, which means this guy equals this number as well. Not much to do there. It's a one-to-one relationship that's happening. And it would be 0.018. So just to, again, touch upon that point about the negative, if you did not put the negative here, you would have got a negative value for this. And then when you would put it into the rate over here, you would have also gotten a negative value for the BR2, which would not make sense because BR2 is a product, so it should be increasing with time and positive. So again, you could catch yourself if you sort of understand what's happening. If you ended up with that negative 0.018 for the BR2, it shouldn't make sense because what that would imply is the product is actually decreasing where the product should be increasing. So again, it's really important to sort of watch the negatives and all that kind of stuff because it does sort of indicate sort of what is happening correctly if you have the negative or the positive. So again, if you happen to have not done that extra negative and ended up with a negative 0.018, what you would technically be saying is the BR2 would be decreasing by 0.018 molarity every second, which would not make sense because this reaction should be heading in this direction. And that means we should be actually making BR2 and not decreasing BR2. So again, important to just keep an eye out on those negatives and those positives because it may not seem like it means something, but it does actually mean something here when you're sort of talking about kinetics. Question on rate expression or how to use rate expression to figure out how everybody is changing. Any questions on any of that? I will say as well that, and if you read your book, I don't recall off the top of my head in your book how it does it. There is another approach that you could do these problems where you just, for example, in this particular problem here, you could just do sort of the stoichiometry part first. So where we converted into, where are we at here? We converted into moles of the BR2 over here. You could then just did a regular sort of mole to mole relationship. So I guess what I mean by that is, I'll just actually write it here in a different color real quick. Try red, that's good. So let's just say, you could have sort of done this as a sort of just a regular stoichiometry problem. So you could have done your 2.184 moles of NOBr. And then, I ran out of room, you could have done your 2 moles of NOBr to 1 mole of BR2 and gone to BR2 first and then divided it by 300 and you'll get the same answer. But this is really what the 1/2 is for. If you look here, right? That is the 1/2, which is what we use here. So if it's easier for you to sort of visualize, you could kind of do these problems as sort of like the stoichiometry part first, like normal, and then just kind of, divide by the time and stuff like that. And it'll come out the same way. And as you can see there, that's essentially where the 1/2 relationship comes from. Again, it sort of builds into the expression, the stoichiometry part of it for you without having to maybe do sort of a separate calculation. But another way you commonly will see people do it is sort of just do the stoichiometry part first and then sort of do the rate part next. And that's you'll come up with the same answer when it's all said and done. All right, any questions on that? All right. So let's just talk about some of the factors that will affect rate, and some of these things we'll talk about as we go through the rest of this chapter. The nature of reactants, so what sort of physical condition they're in has an effect on how fast or slow a reaction may take place. Typically, smaller molecules will react faster than larger ones. Smaller ones, for example, if we're dealing with gases, right, move around faster. Smaller guys in sort of solution move around and are a little bit more free, and they come in contact with each other, and the reactions will occur a lot quicker. Gas molecules tend to react faster than liquids, and liquids faster than solids. Again, for that same reason, gas molecules are constantly flying around, which means they're going to probably constantly come in contact with each other quicker, and reactions would proceed faster. In the liquid state, everybody's floating around, so they're going to float into each other and come in contact with each other, and probably the reaction would obviously occur faster than if you just kind of drop two solids on each other with nothing else involved. Not much is probably going to happen very quickly in that case. If we are dealing with something with solids, if you have more of a powder solid, so a broken up solid spread out, it creates more surface area for reactions to occur on, rather than, if you just have this big solid chunk of something, it's got to kind of work its way from the top through the entire sort of sample. Certain metals will be more reactive than others. So we saw this when we talked about single replacement reactions. Again, right, that is that list, that activity series of metals, where there's sort of like hydrogen in the middle, other metals above and below it. And again, things that are higher on the list are more reactive than things lower on the list, and vice versa going on there. And when we have ions, ions are typically in solutions, and ions are typically free floating, right? Which means they're going to be floating around, ready to basically come in contact with other things, and reactions tend to proceed faster. You don't have to go about kind of breaking a lot of bonds. They're kind of good to go in terms of reactions. So usually will result in a better, faster sort of reaction that occurs. Temperature is a big effect on reaction rates, and Arrhenius has an equation, which we'll see later on in this chapter, which relates the change in temperature to the rate of reaction. But just sort of logically thinking about it, when we increase the temperature, that's pretty much supplying a lot more energy, and everybody gains more energy to perhaps break bonds, start the reaction, and all that good stuff. So typically what we see is if we increase the temperature, the reaction rate will also increase. And in general, not for all reactions, as it says up there, but if you kind of bump up the temperature about 10 degrees Celsius, you'll usually see a doubling in how fast the reaction will occur. And that also means the opposite as well. So if you sort of lower the temperature on the reaction, so if you throw everything on ice and something like that, the reaction typically will proceed at a lot slower of a rate. So again, that's a very common sort of thing. Temperature plays a pretty big effect in terms of how fast or slow something happens. Other things that can affect a reaction rate are things like catalysts. Catalysts are not reactants. They're not products. They're simply substances there basically to affect the speed of a reaction. So they don't get used up either in the reaction. So they're kind of there at the beginning, there at the end. They're really just there to facilitate the reaction occurring, usually in most cases faster. So usually when somebody says, hey, we add a catalyst as a reaction, why did we do that? Probably 9 times out of 10, the answer is going to be we did it to speed up the chemical reaction. Not all catalysts, though, actually speed up a reaction. There are some that are referred to as a negative catalyst. They can actually slow a reaction down. But like I said, probably 9 times out of 10, if somebody's talking about a catalyst or ask you what a catalyst is, they most likely are looking for that answer of it speeds up a chemical reaction. How do they do it? There's different types of catalysts. Catalysts can be homogeneous. And just like we talked about with a homogeneous mixture, homogeneous mixture means it's the same phase throughout. So both the catalyst and what's going through there, the reactants and stuff, are in the same phase. Heterogeneous means that we see some different phases, and that means that the catalyst and the reactants are in different phases. We'll talk a little bit about catalysts obviously later on in the chapter, but just to sort of quickly answer your questions, that's basically what a catalytic converter is in your car. There's usually two parts to it. They have different catalysts in there to help basically clean up some emissions that would go through without it, some carbon emissions and some sulfur type emissions and stuff like that. So there's different types of catalysts that help with a mixture of air and O2 react those sort of products we don't want to come out of the car into the atmosphere. And they're able to do it really more efficiently by having those sort of catalysts in there. That's why it's called a catalytic converter, because inside, your catalytic converter are actually catalysts and some good metals and stuff like that, that help sort of make that sort of reaction of getting rid of certain those pollutants a little bit more efficient, if you will, and occur at the proper temperatures and stuff like that. So we'll actually, I think at the end of this chapter, see a picture of sort of a catalytic converter. And so we'll get back to that question a little bit later on as well. But that's essentially, why people will steal them sometimes, because they have some pretty good metals in there as catalyst. Sometimes you'll see catalyst usually in equations written on top of the equation. There's things like platinum, are sometimes used in some of these metals and stuff like that, that sometimes are found inside, catalytic converters because of that. Other things that can be used as catalysts as well, as we'll see, not necessarily always metals, but, things like acids are sometimes used. And oftentimes in equations, catalysts are sort of written above the arrow there. And that indicates that, again, they're not really reactants or products, or they're just to facilitate it. And really, in some cases, it just sometimes provides like a platform for everybody just to sort of congregate to. And because they all kind of come towards it, they're then going to come in contact with each other a lot quicker than they would if that catalyst wasn't there and they're just kind of flying around going, where are you, type of thing. So you got this sort of centralized area where, oh, I'm like attracted there, and so am I. And then they able to sort of come together a little bit more efficient. And because they're able to come together a little bit more efficient, the end result of that is it usually will basically speed up the chemical reaction and allow it to occur a little bit faster. So we'll again talk about catalysts a little bit more towards the end of this chapter as well. Now, other things that affect reaction rates are things like concentration. So the larger the concentration, usually of the reactants, the faster the reaction will occur. And that's also sort of a simple concept to sort of think about. The molarity is moles of solute over liters of solution, right? And when we think about molarity, really when things react out of this entire sort of expression, it is really just the moles of the solute. So it's really the stuff dissolved in the solution that's ready to react. And the higher the concentration, that means you would have more moles of solute in the solution. And if you have more moles of those guys floating around in the solution, they're bound to come into contact with each other a lot quicker, and thus the reaction should kick off a lot quicker as well. So again, it increases sort of that frequency at which those guys could come together, come in contact with each other, and have a reaction actually take place. Now, when we talk about gases, it is related to pressure, and high pressure means we have a higher concentration. So again, if you remember in terms of gases, when we talk about high pressures and sort of Boyle's law relationship, high pressures means small volumes. So if we have that really small volume, everybody's basically shoved together in sort of that situation. And because gas molecules are flying around to begin with, if we kind of shove them together, there's a pretty good chance they're going to come in contact with each other and again sort of be able to kick off that reaction in a lot faster of an area than if you had a lower pressure, where then the volume is spread out a lot more room for people to fly around. Again, going to take longer for them to come in contact with each other and probably kick off that that reaction. All right. And again, we're going to kind of talk about some of this stuff in a little bit more detail as we continue through this chapter. But the next thing we're going to talk about is actually the rate law. And the rate law basically expresses the rate of a reaction to its rate constant and the concentration of the reactants raised to some type of power. So if we have a generic reaction like what we see here on the screen, A plus B goes to C plus D, we can write a rate law for this, and sometimes referred to as sort of a generic rate law here. But let's just kind of look at what these parts are here. The rate obviously is the rate of the reaction. The K here, the lowercase k, is our rate constant. These are our concentrations of our reactants. And X and Y in this particular case, these are what are referred to as the orders. And X would be the order with respect to A. Y would be the order with respect to B. And you could add these together. If you add X plus Y, whatever those numbers are, it will give you the overall order of a reaction. Now, you may be tempted to think, well, X and Y are probably related to the coefficients, and they're actually not. So X and Y, which are the orders, they're always found experimentally. And what that usually will mean is when you get to a problem such as this, you will typically be given a table. And this table will have pretty much, 3 pieces of information in it. It most likely will have the concentration of the first reactant. It probably will have the concentration of the second reactant. And mainly there's probably not more than 2 reactants usually. Sometimes there's 3. And it will have the initial rates that's happening there. Now, the thing that you may also notice when we look at this rate law is there is nothing to do with the products. So when we talk about the rate law, it's only the reactants involved. So just the reactant side involved. So no products in the rate law, just the reactants. And that's because, again, in these cases, we're assuming that this is sort of a one-way street, a forward reaction heading to the product side. So the entire rate of that particular reaction is based on those reactants coming together to form products. So since nothing's coming back the other way, the whole thing's going to be basically determined by how the reactants are going to come together to basically kick off this reaction and achieve a sort of measurable rate. So when you get this table, you'll pretty much have obviously information about the reactants in terms of their concentrations. You'll also be given things in terms of their actual rates. And you could either look at the table and sort of analyze what's happening with the concentration versus the rates. So for example, you could look at the table and go, well, the concentration doubled, so did the rate. So it's a kind of a one-to-one relationship in terms of how those do it. Or, the rate, the concentration doubled, the rate went up by, say, a factor of 4. So it's like a 1-to-2 relationship sort of thing. Sometimes people have a very hard time sort of visually sort of analyzing those things. So it's usually a good idea maybe to take more of a math approach. And you can take a math approach by using sort of this formula here, that the rate 2 over rate 1 equals k of, say, a to the x, b to the y, divided by k a to the x, and b to the y. So what do I mean by like rate 1 or rate 2? I mean, when you go to that table, you don't have to pick the first and second entry in that table, but you need to pick 2 entries in that table. So let's say, for example, we had in that table, experiment 1, experiment 2, say experiment 3. And for the concentration of A, it was 2, 2, we'll go 4 on that guy. And let's say the concentration of B was 2, 4, and we'll go 4 here. And let's just say that the rate in molarity per second was, just to make up numbers, we'll just go 2, 4, 6, very creative in terms of those rates. Now, when we go to these tables, you'll see a table that looks something like this. What you're looking for is 2 entries in the table. So you're looking for 2 entries in the table where the concentration of one guy remained the same while the concentration of the other one varied. So if we just look at experiments 1 and 2 here, the concentration of A remained constant, concentration of B varied. So we would want to choose those two and kind of put it into our expression here. And if we put it into our expression, the other thing that you typically want to do is go probably the larger rate on top. So I'm going to put everything for experiment 2 up on top, and that would give me 4 equals the K times my A value in that one, which is 2 to the X, and my Y value in that one was 4 to the Y. While on the bottom, I'm going to put everything from experiment number 1, which means my rate was 2, and my A was 2, and my B was 2 as well. So if we look at this, we can then do some math. And the math hopefully will not be too difficult. When I take 4 divided by 2 on the left-hand side, that gives me 2. Now this K on top and this K on the bottom, that is the rate constant. And since it's called the rate constant, although I do not know what the value of it is, I do know it's going to be the same number, which means they're going to cancel. Because I held A constant here, I got 2 on the top to the X and 2 on the top to the X. This X value is going to be the same. Again, I don't know what it is at this point, but I know it's going to be the same. So that means that these are going to cancel. When I divide the 4y by 2y, I end up with 2 to the y when I divide those two. Now I could easily, hopefully, solve that y in this case would equal 1, right? And we would know that for our b, the order would be first order in terms of 1. By the way, mathematically, when you have something like that, like say 2 equals 2 to the y, you can take the natural log of both sides. So if you take the natural log of 2 equals the natural log of 2 to the y, what you end up getting is basically the natural log of 2 equals the natural log of 2, and the y comes down. You can then divide by the natural log of 2 to both sides, equals 1. So if you don't have a really pretty number, sometimes, most of the time, they'll come out to pretty easy to kind of figure out. But basically, you can take the natural log of both sides and then divide them, and you'll get the value of y in that case. What we would then do, and since we're kind of out of time here, but what we would then do is go back to our table. And since we kept A constant the first time, we now want to keep B constant, which in this case would be experiment 2 and 3 would do that. And you can basically do a similar calculation. And that will allow you to get the orders of each of the reactants. And once you get the orders of each reactant, you then can get the completed rate law. And once you've got that, you then can actually figure out the value of K, which obviously we will talk about on Monday for a little bit. Any questions on that? Okay, so we will stop there. Lab today is colligative properties, which is boiling point expression, I think. So we'll talk a little bit about that. Make sure you put here, and we'll talk about some other things as well when we get to lab. So I'll see everybody in about 20 minutes in lab.